Okay, today's lesson is actually the last in our chapter. This is chapter 3, and for the last couple of days we've been studying matrices. Yesterday we learned Cramer's rule, which was a way to solve a matrix system of equations, and today we're going to learn another way to solve a system of equations using matrices. And so we have a little background information. So before we start the notes officially, let's find each product. So I would recommend that you pause and you practice multiplying these matrices together, and you're going to see something interesting happen here. And then when you're ready, resume, and you'll see that I have the answers written down. Okay, so let's first take a look at parts C and D. And we're interested in investigating this matrix that has elements 1, 0, 0, 1. Notice that if you take any 2x2 matrix with elements A, B, C, and D, and multiply it by this other matrix, 1, 0, 0, 1, you just get your original matrix again. And we can see in part D that it doesn't matter which order you put these two in. If the 1, 0, 0, 1 matrix is first or second, you're still going to get your original matrix again. So that should remind us of something that we know about real number properties. If you have the number 1 times A, you just get A. Or if you have the number A times 1, you just get A. 1 is the multiplicative identity. Okay, now we see in parts A and B that when we multiply these two matrices together, we get the matrix with elements 1, 0, 0, 1, and it doesn't seem to matter what order we multiply them in. You see part A and part B, we have the same two matrices, but the order has been switched. We still get the matrix that has elements 1, 0, 0, 1. So that should remind us of a property from real numbers. If you have a number A and you multiply it by its reciprocal, 1 over A, you get the multiplicative identity 1. Now, instead of calling 1 over A the reciprocal, we could also call it the multiplicative inverse. So a number times its multiplicative inverse gives us the identity. So something multiplied by its inverse, in this case of multiplication, equals the identity. So that's the concept that we're going to be working with today. Okay, we're on notes number 14, and we're going to learn a method called the inverse matrix method. But first we need to talk more about this matrix that I'm going to refer to as the identity matrix. We just looked at the multiplicative identity for real numbers, so what is the identity matrix? Well, if you're talking about a 2x2 matrix, it's the matrix with elements 1, 0, 0, 1. If you multiply something else by this, you get the identical thing you started with. What if it's a 3x3? If it's a 3x3, the identity matrix has 1s on the main diagonal and 0s everywhere else. Now you can expand that idea. Here's a very exciting reveal I'm about to show you, etc. You can expand that idea, so if you were looking for a 4x4 identity, it would have 1s on the main diagonal and 0s everywhere else. So just a single diagonal of 1s and 0s everywhere else, and the identity always has to be square. Sometimes we'll call this I sub 2 for the identity of 2x2, I sub 3 for the 3x3 identity, and so on. So in the warm-up, before we started the notes, we saw that there were a couple of matrices that we multiplied to give us the identity. So we would say that those matrices are inverses of each other because their product is the identity. And here's how we can write it. If you have matrix A, the notation for its inverse looks like a to the negative 1 power. It's really not an exponent, it's just a symbol that means the inverse. So if you multiply A by A inverse, you'll get the identity. Or if you multiply A inverse by A, you'll get the identity. The order doesn't matter when you're multiplying inverses. Now, suppose you want to know how to find the inverse of something. So for example, if you had real numbers and you have the number 3, how do you find its multiplicative inverse? Well, that's just the reciprocal, 1/3, 1 divided by 3. So what about matrices? How do you find the inverse of a matrix? So I'm not going to prove it in general, but I'm going to give you an example to kind of make a convincing argument. So let's take this example. Suppose we have matrix A, and you don't have to write this part down. You can just watch. We'll get to a formula, and you can write that part down. Suppose this is our matrix A. We know that if we were to multiply A by its inverse, we would get the identity. The question is, what's the inverse? Well, because I don't know yet, I'm actually going to use systems of equations to figure out the values of A, B, C, and D, like algebraic methods. So if I multiply the first row and the first column, I should get a 1. So that means I have 4A plus C equals 1. And if I multiply the first row and the second column, I should get a 0. So that means I have 4B plus 1D equals 0. And if I multiply the second row and the first column, I should get 0. So that means I have negative 3A plus 7C equals 0. And if I multiply the second row and the second column, I should get 1. So that means I have negative 3B plus 7D equals 1. So what we have here are two systems of equations with two unknowns in each. So let's go ahead and solve these systems to figure out the values of A, B, C, and D. Okay, in the first system, I'm going to take the first equation and multiply it by negative 7. So negative 28A minus 7C equals negative 7. I'm going to leave the second equation alone, negative 3A plus 7C equals 0. And I'm going to add these to eliminate the C. So negative 31A equals negative 7. So A is 7/31. Not a very user-friendly number, but it's actually good when you're trying to figure out patterns and things if your numbers are not very simple, if your numbers are unique. Okay, so let's go ahead and keep going and find the value of C. So 4 times A plus C equals 1. So 28/31 plus C equals 1. So C equals 3/31. Okay, now let's go over to the other system and find the value of B and D. So once again, I'm going to multiply the first equation by negative 7. Negative 28B minus 7D equals 0. Leave the second equation alone. Negative 3B plus 7D equals 1. Add these together. Negative 31B equals 1. So B is negative 31, or negative 1/31. And then to find the value of D, 4 times B plus D equals 0. So D must be 4/31. Okay, so what I want to do is put these together in a matrix. So the elements A, B, C, and D are 7/31, negative 1/31, 3/31, and 4/31. And what if I factor out 1/31, the scalar? Then I have that multiplied by 7, negative 1, 3, 4. So what I'm curious about is how does this relate back to the original matrix A? So this is A inverse. Okay, so here's what I want you to notice. The original matrix A had elements 4, 1, negative 3, 7. Look at A inverse. Notice that you have the 4 and the 7 on the main diagonal, but they have switched places. And then look at the other diagonal. You have the opposite of the original number and the opposite of the original number. Now, you could go through several examples and you'll see that every single time. Of course, we don't have time to do it over and over and over again, but if you want more convincing, you can try it on some other random problem that you make up. But what about the number 1/31? How does that come into play? Or how about just where does the 31 come from? Well, if you remember from last time, we found determinants, and the determinant of A is 4 times 7 minus 1 times negative 3. So that would be 28 plus 3, and that's 31. So the inverse is 1 over the determinant of A multiplied by some kind of rearrangement of the elements of A where we switch the numbers on the main diagonal and we take the opposite of the numbers on the other diagonal. So here we have that in writing. Now I'm calling A just a generic matrix, 2 by 2. A, B, C, and D are its elements. And so to get its inverse, we take 1 over its determinant and multiply that by, notice that the numbers on the main diagonal have switched order, and notice that the numbers on the other diagonal are now the opposite. Now this will work as long as the determinant, AD minus BC, is not equal to 0. If the determinant equals 0, you're going to have 1 divided by 0. That will be undefined. So not every matrix has an inverse. Not even every square matrix has an inverse. Just like not every real number has an inverse. Can you think of a real number that has no inverse because there's nothing you can multiply it by to give you 1? I hope you're thinking of the number 0. Okay, let's find the inverse of matrix A. So go ahead and give it a try using that formula, and then we'll check and see if we agree. So to find A inverse, I'm going to find the determinant of A and put that in my denominator outside the matrix. So what's the determinant of A? 3 times 8 minus negative 3 times negative 5. That would be 24 minus 15, so that would be 9. So the determinant is 9, so we have 1/9 on the outside. And then for the inside, we're going to switch the places of the 3 and the 8. And then we're going to take the opposites of the other two numbers. Now we can also multiply the 1/9 through. So if you were using your calculator to find an inverse, it wouldn't have the number factored out, it would multiply it through. So that's equivalent to 8/9, 1/3, 5/9, 1/3. Now suppose you want to check to see if that's really the inverse. What can you do? Well, you can take that answer, multiply it by matrix A, and see if you get the identity matrix when you multiply. Okay, now suppose that we have this problem. Some 2 by 2 matrix times some other matrix X, which must be a 2 by 2, right? So that when we multiply a 2 by 2 by a 2 by 2, we get a 2 by 2. So X is some 2 by 2 matrix. We want to know what it is. This problem is similar to this other problem, a simpler problem like this. If I have 3 times X, I get 12. Well, I want to know what X is. What would you do if you had to solve that problem? You would probably say, I would divide both sides by 3. But what if division did not exist? What if we didn't have a word for that? Because with matrices, we don't have a division. Instead of calling a division, you might say, okay, fine, then I will multiply by the inverse. And the inverse is the reciprocal. So I will multiply both sides by 1/3 because I know that 3 over 3 is 1. 3 over 3 is 1. 1 is the identity. 1 times X is just X. Bada boom, bada bing, I get 4. So let's do something like that with matrices. So there is no matrix division. So there is no way I can just divide both sides by this matrix. Sorry, we don't have that. Instead, we need to know what can I multiply the matrix I have by so that together they give me the identity. Because the identity times X is just X. So this is the plan. Figure out what to multiply by so that you just get the identity. You know what? We know what that is. That would be the inverse. Now, of course, you can't just multiply one side of the equation by that without multiplying the other side of the equation by that. Just like over here, I multiplied both sides by 1/3. So what we're going to do is we're going to do something called left multiplying. If I multiply the left side of my matrix equation by something, I have to multiply the left side of the other side of the equation by something. the left side of the equation by something. I think I said the word side a few too many times. Okay, the reason why you have to put it on the left on both sides is because we know that matrix multiplication is not commutative, meaning the order could change things on you. So let's go ahead and find that inverse. Let's say this is called A. Let's find A inverse. Okay, so let's find the determinant of A. That would be 15 minus 14, so that would be 1. Okay, that's nice. We have 1 over 1 on the outside. That's lucky. Then we switch the places of the 5 and the 3. We take the opposite of the 2 and the 7. That's our that's our inverse matrix. So that's going to go on both sides. But on the left, we know what this product is. That product is the identity. And the identity times x is just x. So all we really have to do, what it boils down to, is after you find that inverse, multiply these together. So let's do that. So remember, across a row, down a column. So 5 times negative 2 is negative 10, plus 2 times 3, 6. So that's negative 4. And then 5 times 4 is 20, plus 2 times negative 1, negative 2. So that's 18. And then 7 times negative 2 is negative 14, plus 3 times 3, 9. So that's negative 5. Hope I'm not making any mistakes here. 7 times 4 is 28, plus 3 times negative 1, negative 3. So that's 25. So that tells us that we have, for x, matrix negative 4, 18, negative 5, 25. Okay, the good news is this is the last lesson of the chapter, and the bad news is we still have a ways to go. There's another big deal concept here, so I'm going to stop this video and make a part 2.